The lecture today is going to be about the precise definition of a limit. Okay, in the previous lectures we have talked about finding a limit of a function, and our approach has been more experimental or intuitive. So for example, if I had a function f of x say is equal to x squared, and I was asking what is the limit of f of x as x approaches 3, we have been essentially saying, well, when x comes very close to 3, squaring it will create a number that's very close to 9, and that was enough for us. Well, those of you planning to go on to more advanced mathematics will require a bit more understanding of this topic. So we are going to go and dig into this a little bit more and give an exact definition of what is it that is involved here. And we'll have a bit of a philosophical discussion if you wish. Okay, here we want to make sense of the following. What do we mean when we say limit of some function f of x as x approaches some given number a is equal to some final number L? What is the meaning of this? So we might as well make a title for this. What is the meaning of this expression? Okay, the traditional definition for this uses some Greek alphabet. Let me just introduce you to these before we go on, so that you will be able to read my handwriting. Of the Greek alphabet, what they use here is one letter epsilon, and another one is the letter delta. I'm sure all of you members of various Greek organizations, you know these letters, typically written in capital, but for some reason mathematicians like to use these letters every now and then. So we are going to use them now. Later on there will be a couple of other letters you'll use for your trigonometry, and you'll be as Greek as anybody else. Now, what is let's go back to the serious stuff. What's the definition of this? The definition is the following. We say limit of f of x as x approaches a is the number L if for any positive epsilon, for any epsilon that is positive, there is another positive number, there is delta, a positive number, such that the difference between f of x and L, which is such that the difference between f of x and L, which is the absolute value of their difference, such that that quantity is less than epsilon, that given first number, whenever x itself is as close to a as delta, that that is, the difference of x and a is less than delta but larger than 0. Okay, let's see what we understand by this very peculiar sounding definition. So among all the sentences you hear in the calculus 1, 2, 3, this is probably the hardest one to digest as to what it says. We are just trying to explain what the limit is, and somehow that definition turns out to be a rather complicated sounding expression, but in reality there is no way of simplifying this thing, so we need to get used to this and understanding as best as we can. So read it several times, try to see if you can understand it a little bit on your own, and then we continue. Let's go ahead and draw some pictures, and perhaps the picture is going to help us with this. Because suppose I have a function in this coordinate system, our function y is equal to f of x. We are investigating the behavior of this function when x is some number, say, close to a. So here is where the function is at. We are saying that when x comes close to a, the function comes close to its limit L. We want to understand that. Well, there are two other quantities here. One is called epsilon, one is called delta. What do they do? One way to think about this thing is about by using the concept of laying traps. Let's see, what's a trap here? A trap on the vertical axis y will be a region that starts at L and goes by epsilon above and epsilon below. So here I lay my trap. I go epsilon above and epsilon below. So this point is going to be L plus epsilon, and this point is going to be L minus epsilon. So the game starts by somebody laying a trap like this by going above and below the claimed limit, and then asking you to find another trap around A, such that when x is inside that trap but exclusive of A itself, the value of a function, that is the y, is inside of this trap. So on a nice looking curve like this, it's not so hard to figure out how to lay the other trap. We go straight to the function, and then go down. Now we want to figure out a region inside of this, symmetrically placed around A, such that if we live inside of that region, the value of the function, the y of it, is going to be placed inside of this trap. So you want to lay a trap here. How big do you think you can make it? Well, for example, if I go as far as here, excluding the A itself again, if I lay a trap here, that is, I restrict my x's to live inside of this orange region, so then my y is gonna live in between these two horizontal black lines here. So I start going up to show to you what happens if my x is limited to this region. My y will be inside this black trap. So here I go up here too. All of my y's, here are all the y's I will get with the exclusion of this point, is in between these two horizontal black lines. Now I can make my trap here a little bit bigger. For example, I could have, let me use another color, say I could have come by delta to the left and delta to the right by a certain amount to the left and right. So I come here, I can go, and I still live inside the required region. So visually it's not a hard game to play. If you look at your picture and see how far you can go to the two sides of A such that your output will be inside of this given region, then you have discovered what your delta is going to be. Now you have to be careful. Sometimes, like if I take this and move it all the way to the end of the region that I see, suppose I take this green line and just move it to here, say, then I have to go by the same amount on the other side. Well, I see what the problem is. I'm gonna leave the required region. So when you look at both sides of this point A, your delta should not be so big as to take you outside of this black region here. Like for example, if I had started here and I go up, obviously the resulting y value is not inside the black region that is required in this case. Let's go ahead and take a particular problem and practice it with some given numbers, and that would be perhaps more understandable than the picture I just gave. Here I pick one of the problems. It's studying the function. Here's the function. If you take a specific function, f of x is equal to radical x, and we are also aided by a picture here. Let's draw a picture. Here is radical x. We are expected to do the following. We want to show that we really want to show that limit of radical x as x goes close to 4. What's that limit? Well, when x comes very close to 4, square root of that stands to reason has to come close to 2. That simple observation, we want to turn it to some precise definition, see what that means. As a first attempt, we go ahead and here let's go ahead figure out where is 4 and 2. Suppose here is 4 and for sake of this picture assume that this is 2. Now what we want to do is to play this epsilon delta game. You remember how we were setting things up. For sake of playing with just straightforward numbers, let's assume that our epsilon is say 0.4. So 0.4, suppose 0.4. So I'm going to take epsilon to be say 0.4 just to get started. So we are laying a trap here by going 0.4 above and below 2. So this is going to be 2.4. This is going to be 1.6. Now the question is the following. If I go back to the function, if I want to limit myself to live around 4, how far to either side of it can I go such that if I start at any of those locations and come back to the y-axis, I'll be stuck inside of this trap? Well, in this picture it's quite obvious that you don't want to go as far as here. If you choose an x here, your y is not going to live inside this trap. If you choose an x here, of course, again, your corresponding y is going to be outside of this trap. So where is the beginning and end of these this region? Well, take one, this is your y value. This is your result of square root of x. So I say if square root of x turns out to be 1.6, then, well, x is going to be 1.6 squared. That is 2.56. That is this end of this region. This has to be 2.56. Don't go below this because otherwise you'll fall outside. How about the other side? Well, in the other side, square root of x has turned out to be 2.4. So x itself is 2.4 squared. What is 2.4 squared? So 2.4 squared, I guess it is 5.76. Let me double check quickly. That is 2.4. Yes, that is 5.76. So this is 5.76. Okay, here's a simple answer. If you live here, if your x is between these two numbers, your y will be between those two numbers. That observation as yet doesn't prove that the limit is 2. There's still a lot more to go, but we're just giving a simple example. Next improvement that we have to make on our answer is to come up with a symmetrical region. Symmetrical means you have to go same distance to either side. So how far is it from here to here? You see from here is 1.76. How about this one? So how did I get that? 5.76 minus 4 is 1.76. How about this side? This side I have 4 minus 2.56, and that's going to be 1.44. So this side is a little bit smaller than that. The way our definition is set up, and that's just by tradition, that we are going to go same amount to either side. So to be agreeable with that definition, we are really going to need to go here as far as 5.44 and as low as 2.56. Why did we do this? Because now either way I am going by the same amount. This is both of them is 1.44. So now we say if x is within this orange region, if I am right here, my y is going to be inside the originally designated region. So here we say if. Now how do I say that x doesn't deviate by more than 144 from 4? If x minus 4 is less than 1.44, then radical x minus 2 is going to be less than 0.4. Let's go look at this picture here again. If x, the distance of x from 4 is less than 1.44, then distance of square root of x from 2 is less than 0.4. Now, there are several other things to talk about. One is that in the definition of limit, this is given to you as a certain parameter. It's called epsilon. For whatever that parameter is, you have to come up with this delta. So for example, in this problem, I could make this trap tighter. I could go up and down by 0.1, and then I ask you to go through all of this thing all over again and design the trap on the x-axis so that it will have the same property. And then again, I can make the trap here even smaller and pose the question to you again and expect you to come up with an answer for that case. So in the definition of limit, we really say whatever I decide to be the size of the trap on the y-axis, you should be able to tell me quickly the size of the trap on the x-axis. So we don't need just the arithmetic answers. We don't just need specific numbers, but we really need a procedure that whatever this number is, you quickly determine this number with the property that is required. So that's one thing to keep in mind. Item 2 to keep in mind is that we have an additional discussion here that we keep x away from a. X minus a is larger than 0. What's the reason for that? The reason is that limit doesn't have anything to do with the value of the function at that point. We don't really care about what the value of f at a is, and for that reason we don't let x to be a itself. Okay, just to be able to handle some of the rather unusual problems, we don't let x to be a itself. It is always staying away from that so that the limit procedures will go through without any problem. Typical problem you see, like the ones that you have seen in the previous sections, if you take x to be your ultimate limit number, a division by 0 will occur, or some other problem might occur. Just to stay clear from those problems, we keep x different from a, and the simple way to do that is to require that the distance should be larger than 0. So this is rather technicality that comes on the side of all of these problems. Sometimes you can ignore it without any difficulty, but in many examples you cannot do that. Now let's go ahead and practice this problem perhaps in the context of another example. Let me ask you to do the following. Let's just take the same problem that we just did, and I tell you to make the trap smaller and come up with the answer. So again, we consider this same function. Here was radical x. We are still concerned about the same point, say 0.4. at which we suspect the limit is going to be 2. So here is my 2. I go do the following. I say, okay, I'm going to lay a tiny trap here. I'm going to go as far as 2.1 up here and as low as 1.9 down here. So 0.1 above and below. So I'm taking my epsilon to be, let me use a different color here. So I'm taking my epsilon to be 0.1. I have gone 0.1 above and below my target number. Now that's going to make our picture rather hard to see. You tell me how far to the left or right of 4 can I go so that my output still live inside of this this purple looking region. So here I go down here, and this picture is not to scale, so we are going to have a bit of a hard time. First, where is this? Okay, can you pause for a moment, come back and tell me where are the 2 endpoints of this interval? Okay, did you pause and come back now? Here our recipe was very simple. You just take the output of your function radical x, set it equal to the 2 limits that you have, 1.9 in this case. That tells you x is going to be 1.9 squared. 1.9 squared, I guess last time I checked was 3.61. Let me see, 1.9 squared, 3.61. So this number here is 3.61. The number above, okay, now I have radical x. Here's my x. Square root of that ended up being 2.1. So x becomes 2.1 squared. You square that, you get 4.41. So this number here is 4.41. So how far to the left have I gone? The amount to the left from 4 to 3.69, that is, you subtract them and you get 3.9. How far to the right have I gone? I have gone by 0.41. Okay, once again, we want to arrange a symmetrical region around this, just by definition. So we go by the smaller number to make sure we are not exceeding the boundaries. So I say if x minus 4 is less than what number? Okay, this is the setting the size of the trap on the x-axis. You take this small enough so that you can guarantee that the result of the function will be inside this trap. So we want radical x minus the limit value 2 to be less than, well, we are allowing up or down by 0.1. So what was this? Again, the answer turns out to be 0.39. So we say if x minus 4 is less than 0.39, then radical x minus 2 is less than 0.1. So up here we had this. If this is less than 1.44, then radical x differs from 2 by 0.4. This was a more forgiving trap. This was a wide trap. I'm coming here making the trap much tighter. As a result, this is going to be also much tighter. Now the limit definition says if you can play this game for any positive number here, regardless of how tight I make this trap, you can make another trap on the x-axis, then you have succeeded in proving that this number is really the limit. 2 is really the limit of radical x as x comes close to 4. Now, for many of you, when you come across all of this work and all of this discussion, just in your mind, just to take a square root of 4 and figure out that is 2, the whole thing looks rather ridiculous. Why are these people doing this? That would be a question that you'll be asking, and you would want to get away from this. Let me tell you that your experience is not uncommon. Anybody who comes across the definition of limit first time around feels as if he is just hitting a mountain. It takes a while to understand the definition and to work with it. Second question comes around, why is it that they take so much work to produce something so trivial? Well, to give you an answer in that, let me tell you that the examples we choose to talk about the situation are the ones that are very familiar to you, and that familiarity, well, breeds contempt, because you think the answer has to be so easy to get, while we are taking so much time and effort to arrive at our answer right here. To justify to you that this approach is not just busy work, let me give you a bit of history. What happened in mathematics 2-3 centuries ago was that people came across several puzzling situations. There were problems springing out here and there which did not look intuitive at all. Certain assertions were being made that did not correspond to everyday notion that the people had. So that shook everybody's confidence in the mathematics that they were using, and they were forced to go back and lay a very solid foundation on which they could go ahead and build everything and be sure of things that they are saying. Now, the only way to convince you that all this effort that we are spending here is for a good cause is to talk about those puzzling situations. Well, those puzzling situations requires a little bit of advanced mathematics, and they are a little bit out of our reach. But just to give you a flavor of what is involved here, let me digress and give you the reason for all of this. Why do we go through so much effort for doing something that looks to be so trivial? Well, probably the only one of these puzzles that you come across in the course of calculus is something that you will see in calculus 1 or calculus 2, excuse me, related to so-called series. What are series? Let me just briefly mention to you what a series is supposed to be. Well, suppose I start with the number, say 1, and then I add half of it to it, 1/2, and half of what I just added, 1/4, and half of that again would be 1/8, half of that is 1/16, and so on. So series is what you get by adding numbers that are obtained from some formulas, and you take these numbers and just keep adding on without stopping. So it's in fact a sum of infinitely many numbers. How do we guarantee that this whole thing makes sense? Well, that's one of the reasons that the notion of limit is necessary. Well, this one by itself is still rather intuitive. Let me explain to you what the answer is. Suppose I draw a straight line, and say this is 0, this is 1, this is 2, say this is 3, and so on. This is my straight line. We are trying to figure out what this sum is going to be. Let's go ahead and figure it out. Here is my first installment. Here's 1. Next installment is a half. So here's a half. Notice this 1/2 is half of my destination to the next whole number 2. Now, what about this? 1/4. 1/4 is half of, as you notice, is the half of leftover row to 2. How about 1/8? 1/8 is half of this thing again, so that is 1/8. Let me write these numbers on top of it. The first step what we took was 1. Next step we took was 1/2. Next step we took was 1/4. Next step we took was 1/8. As we add up all of these steps, can you guess what the total is going to be? So first step we took, say, 1 foot long, the next one is a half a foot long, next one is a quarter of a foot, next one is an eighth of a foot. At the end of this trip, where would you be? Noticing that every time your step is half of your distance from 2, you see that you come closer and closer to 2. So this series adds up to 2. Adding numbers in a series becomes a preoccupation for you in Calculus 2. You will figure it out how to define this thing as a limit. A limit of summation at this type, it turns out to be 2. Okay, there isn't much of a big puzzle in this one. Some philosophical discussions maybe, but doesn't look all that striking to anybody who hears it. What is it that is striking? Suppose I give you slightly different series. Here's a series. I start with 1 minus a half plus a third minus a fourth plus a fifth minus a sixth, and so on. You add and subtract reciprocals of whole numbers and investigate that series. Let's go ahead and draw this one and see if we can comprehend what's going on here. I draw the real number line. We really don't need all of this, but I make it very big so that we can see what's going on. Here's my 0. Let me take my 1 all the way far away. So imagine somebody who's making a deposit in a bank is putting $1. So here's add $1. Next day he goes and takes 50 cents from this account. So we go in the negative direction. So this first one I was adding $1. Next one I am subtracting 50 cents. Instead of 50 cents, let's write half $1. So by now, how much do I have in my account? 1 minus a half, I have 50 cents. On the third day, I go ahead, so I'm right here. I go ahead, make a deposit of 1/3 of $1. So 1/3 of $1 maybe. I came to this point. So 1 minus a half plus a third. On the fourth day, I go spend 25 cents. So I'm going back, excuse me. So here's minus a quarter. So that was plus a third. And so on. We keep playing this game. Next day, I go ahead and make a deposit of 20 cents. That's 1/5 of $1. and then again next day I go ahead spend $6. So picture looks like this. Let me try to draw it. I am spending $1, depositing $1, coming back by half, adding a third to my account, subtracting a fourth from my account, adding a fifth, subtracting a sixth, and so on. So you see that I'm doing this kind of a zigzag. Always either zig is smaller than the zag, or the zag is smaller than the zig. However it is, I'm going back and forth, never going to as far as the previous. The oscillations are getting smaller and smaller every time I'm depositing or spending one somewhat less than the previous, and eventually my money settles down to somewhere in between all these oscillations we have seen. That's going to be the eventual amount that's going to be in my account. Now in Calculus 2, they are going to tell you how to figure out exactly what that amount is. That's one of the good problems there. That is still not the challenge. That is just straightforward. You're adding and you're subtracting until you settle down to some number. Now here comes a challenging observation, the situation that puzzles everyone, one of the puzzles. I claim that by mere rearrangement of these deposits and expenditures, I can make my final balance to be whatever I want it to be. Okay, were you puzzled by that at all? Let me restate this. You have, imagine this is like a checkbook. You are putting certain money in, and you are removing certain money in certain other days. I'll be putting the same amounts in and making the same withdrawals as before. I'll just change the order that they are going to happen. Okay, same deposits, same withdrawals, but I'll just rearrange the days I'm making deposits and the days I'm making withdrawals. And by simply doing that, I can make my final balance to be wherever I want it to be. That is, if I wish, I could be as rich as the richest man. I can make this final balance to be $1 million if I wanted to. How? Well, it takes a little bit of work to show how that can be done, but that was one of the early puzzles. Anybody coming across this will be surprised. How can that be? That you're adding and subtracting the same set of numbers. You have merely changed the order of summation, and you end up by a different answer. So this situation is in contradiction to something that you learned from back in elementary school, that addition is commutative and associative. In short, if you are adding three numbers, you learn that it doesn't matter in what order you make your addition. So if I write it C plus A plus B, the sum is the same. We are not changing that. Addition still gives you same answer regardless of how you're adding your components. We are simply going to say that is only valid in certain circumstances, and some others that is not valid anymore. Here is a very interesting case where you can rearrange all of these things and make the answer to be a different one. So if that is enough of a puzzle or a challenge to you, you will be motivated to learn about limits as accurately as you can. If you don't care about such puzzles, it will be almost impossible to motivate the topic and convince anybody to go through this definition. If you have a hard time with the definition, let me give you a consolation. It took mathematicians perhaps about 100 years to come up with this sentence. And it cannot be simplified to anything. Any attempt at simplifying this thing has created unsatisfactory results. So you have to kind of bite the bullet, and then just try to live with this definition and understand it as best as you can. Let's go back to our regularly scheduled program and get out of this side remark that I had over there and do some of the problems that you need to do at the end of this section. Here are some of the questions posed to you. For example, you might be asked to prove that the limit of (2x minus 1) as x approaches 3 is equal to, what's that equal to? When x comes very close to 3, what is 2x minus 1 close to? Of course, that is close to 5. Okay, that's simple observation. We want to actually prove it. How do we prove it? First, for this problem, you better draw a picture, and okay, 2x minus 1. Let me take this thing to be 1, 2, 3, 4, and here's 5, and minus 1, 1, 2, 3. Drawing this picture as carefully as we can. At 1 we are at 1, at 2 we are at 3, at 3 we are at 5. So we have a curve this is the graph of y is equal to 2x minus 1. Here we are hovering around x equal to 3. We are hoping to prove that the limit of this function is 5. What was the idea of limit? The idea was that you set a trap here, so you go by epsilon amount, typically a tiny number, to the right, to above or below. So this is going to be 5 plus epsilon, and this one is going to be 5 minus epsilon. So the only way this is different from the previous examples we did is that instead of a specific number, I'm going above and below by epsilon. Let's see if we can succeed in handling it with a letter as opposed to a number. Now I want to go back from here to x. So what is this? In the previous examples we didn't use epsilon because the algebra is a bit more complicated, but since our function here is an easy function, our life is going to be a lot easier. So we are going to say here our y value, here's the y-axis, our y value is 5 plus epsilon. Let me just write 5 plus epsilon is equal to, let me use a stronger color, 5 plus epsilon is equal to 2x minus 1. What do I expect to get? I expect to get x. So I bring 1 to this side. 5 plus epsilon plus 1 is equal to 2x. So 6 plus epsilon is equal to 2x. So that tells me x is 6 plus epsilon divided by 2, which tells me x is equal to 3 plus epsilon over 2. What did I find here? I found here as 3 plus epsilon divided by 2. Now go ahead, do the same thing from the other side. That is, if I start at 5 minus epsilon, what would I end up at? So here is another parallel problem to solve. From the other end of the trap, 5 minus epsilon, what kind of an x do I get? Go ahead and do this thing. What do you think we are going to get? For straight lines, we get a very simple recipe. This was 3 plus epsilon. This becomes 3 minus epsilon over 2. So this one becomes 3 minus epsilon over 2. We have gone by the same amount to either side. That's again a property of straight lines. Step to the right or step to the left. Here's epsilon over 2. In the definition of limit, what did we need? We needed to specify the size of a trap here, such that if we live inside of this trap, our y is going to live inside of that trap. The size of the trap here was specified by delta. Delta is the amount you go either to right or left. In this case, the amount to the right and left is the same amount, and we can pick either of them as delta. So I say choose delta to be epsilon over 2. It's the size of the trap here. Now say if x minus the number, central number here, is less than delta. Delta itself is epsilon over 2. If x minus 3 is less than delta, then f of x, who is our f of x? F of x is 2x minus 1, the function we are investigating. Then 2x minus 1 is within the epsilon of the target number 5. Epsilon 2x minus 5, 2x minus 1 minus 5 is less than epsilon. So this is playing the role of our f of x. This is playing the role of our L, is the limit. This is playing the role of our delta. Is this true? It's obviously the case. Let's go ahead and simplify this. It is saying that 2x minus 6 is less than epsilon. Is it true that when x minus 3 is less than epsilon over 2, then 2x minus 6 will be less than epsilon? Is that true? Yes, it is true. Why? Just go ahead, take this inequality, multiply it by 2. Here you are saying x minus 3 is less than epsilon over 2. You can go ahead and double this, double the right hand side. You can always multiply two sides of an inequality by any positive number. Well, what is twice x minus 3? That is same as 2x minus 6. What is twice epsilon over 2? Well, that is just epsilon. So what does this show? This shows that if x is within epsilon over 2 of 3, then 2x minus 1 is within epsilon of 5. And that is exactly what the definition of limit is. So we have shown that 2x minus 1, when x comes very close to 3, becomes 5. Okay, go ahead and do a few problems at the end of this section related to this. I'll go ahead and say a few words about another definition that is mentioned in the text. You're not going to see it in the exercises right now, but it's good to see it, the definition itself. We had the issue of infinite limits. an example of that was something like this. Suppose I have the function f of x is equal to 1 over say x minus 2 squared. Let me make it x minus 3 squared. What is the limit of f of x as x approaches 3? Well, as x approaches 3, denominator becomes a very small number. When you square it, it's a positive small number. Reciprocal of small number, positive small number, is going to be infinity, plus infinity. Okay, that has been our intuitive approach to this. When x comes very close to 3, this thing goes to plus infinity. But what is our definition? Okay. Infinite limit refers to the situation like this. When you are taking a limit and your limit turns out to be infinity. What does that mean? So here we want to describe what does it mean to say that limit of some function as x approaches some specific location is, say, plus infinity. We want to have a precise definition for this thing. That means given any number m, there is another number, a positive number, again called delta, such that f of x is larger than m whenever x is within delta of a, whenever x minus a is less than delta, and again as before larger than 0. So what is the sense of this definition? Let me try to explain it by drawing a picture. I try to squeeze the picture here. When you have a function like this statement is equivalent to saying that when you come very close to 3, f of x breaks through any kind of a ceiling you try to put on top of it. Okay, it breaks through any kind of a ceiling that you put. In a picture, that ceiling is played by this m. Wherever you like to put a ceiling, whatever this m is, as you come close to that promised number, that the central number in your limit, like in this case was that 3. As I come close to that 3, so here's my 3, the function is going to break through that ceiling that I'm putting around it. If you give me any ceiling, I can find a trap here small enough such that when I have entered inside this trap, I have already broken through this ceiling and have left, like the picture might look like this. So this trap that I'm laying here, I'm guaranteeing that as soon as I enter this trap, I have exceeded that ceiling and have gone through positive infinity. So this number m that we use by problem itself naturally turns out to be a positive number. So sometimes in the definition they say for any positive number, but for any number, if we had said given any number, it would still do. So why is it that we are excluding? What's the reason that we are saying larger than 3? So in this problem itself, we never let x to be exactly equal to 3, because division by 0 is just not defined. To stay away from all those kind of complications, we always have this absolute values larger than 0, so we just don't go overboard and insist on doing any calculation at the point at which the function itself may be undefined. Whatever is happening at 3 itself is irrelevant. We are looking at the problem in the sense of a limit as opposed to calculating a specific value. So that was the definition of a function going to plus infinity. There is a similar definition for a function going to minus infinity. You go ahead and read the definition. All that happens is that this is negative number and your inequality is in the other direction. So instead of a ceiling to break through, you will have a floor all the way down here, and your function is falling through that floor. No matter how low you take the floor to be, the function still goes lower than that. There are still other kinds of infinite limits where x itself goes to infinity and the limit is also infinite. Perhaps we come to those type of definitions later on, or you could read about it yourself. Once again, students very serious about mathematics need to read section 2.4 as carefully as they can and plan for themselves to actually spend the whole semester to digest just that single section by itself. For other of you, I'll expect you to be able to handle problems like I just did today, and then we are going to move on to more concrete examples in applications of calculus and less of philosophical topics as what we saw today. Okay, go ahead and do the problems. Good luck and God bless.